In the previous lecture, we have seen the covariant derivatives of covariant and contravariant vectors. And in that lecture, you have actually seen that when we find the covariant derivative of a covariant or a contravariant vector, then you get tensors of second rank. You must have an idea that when you talk about the covariant or the contravariant vector, they are actually tensors of first rank. But when you find the covariant derivative of tensors of first rank, the result is tensors of second rank. Okay. So now we are going to see the generalized process of covariant differentiation in this lecture. It means now we will talk about the process of covariant differentiation of tensors of higher rank. But one thing is fixed. You will see that whenever we will find the covariant derivative of a tensor of a particular rank, the result will be definitely a tensor whose rank will be greater than by one of the previous tensor. It means if you consider there is a tensor, either a mixed tensor or a covariant tensor or a contravariant tensor whose rank is, let us say, k, and you find the covariant derivative of that very tensor, definitely the result obtained will be a tensor of rank k plus 1. Okay. So after covariant differentiation, the resulting tensor is just of the rank which is one more than the original tensor. Okay. So for getting the general result, or how we can find the covariant derivative of a general tensor, we consider again a simple situation. Let us consider a mixed tensor, a superscript j and subscript k. It means here j is the contravariant index, and k is the covariant index. And this is a tensor of rank 2. Okay. You will see when we will find actually the covariant derivative of this tensor ajk, definitely the resulting tensor will be a tensor of rank 2 plus 1, that is 3. Okay. But how we can find the covariant derivative and how we can say that the resulting tensor is a tensor of rank 3, you can see now. And for this, first of all, let us see the transformation law in accordance with which this second order mixed tensor will get transformed. You know that if a prime mu nu, where mu is the contravariant index and nu is the covariant index, if these are the components of the tensor ajk in the prime coordinate system, then in accordance with the transformation law of tensor, you can write that a prime mu nu is equal to ajk times del x prime mu by del xj times del xk by del x prime nu. Okay. This is the obvious transformation law. Now to get the final result, we will have to do some algebra, and so you must remember all those steps which I will talk here. So first of all, let us take the inner product of this equation 1 by this partial derivative del xj by del x prime mu. Okay. It means see here, the first partial derivative in the expression defined in equation 1 is del x prime by mu by del xj. So remember this technique. You have to take the inner product of this equation 1 by this partial derivative, which is just reciprocal of the first partial derivative contained in this equation 1. Okay. So you can see after taking the inner product by this partial derivative, our LHS will become like this. This is A prime mu nu times del xj by del x prime mu, and that will be equal to AJK at each, and del xj by del x prime mu, we are going to take the inner product by this partial derivative, and the remaining factor is at each. But now you can see the product of the first two partial derivatives, that is del xj by del x prime mu and del x prime mu by del xj. Actually, this product will be equal to 1. For understanding, you can say that this del x prime mu in numerator and del x prime mu in denominator will cancel, and del xj in numerator and del xj in denominator will cancel. Although it is a wrong statement, but for remembering this, you can say like this. Okay. So the RHS becomes the mixed tensor AJK times del xk by del x prime nu. Okay. Now we will differentiate this equation 2 partially with respect to this x dashed nu. Okay. With this x dash nu, let us differentiate this equation 2 by partial differentiation. Okay. Now you can see in both LHS and RHS, there is a product of two functions or two factors, you can say. So when you will do the differentiation, you must have to remember the law of differentiation or rule of differentiation for product of two functions. So following that very rule, you can write that the terms in LHS will be del A prime mu nu by del x prime nu times del xj by del x prime mu. In fact, here in LHS, first of all, I have differentiated this first factor and the second factor is at each. Now let us keep the first factor A dashed mu nu at each and operate the operator, differential operator, on the second term. And when you will do it, your result will be del 2xj by del x prime nu times del x prime nu. Okay. And that will be equal to, now see the RHS of this equation 2. Okay. And you can see this will be del xk by del x prime nu times del ajk by del xl times del xl by del x prime sigma. In fact, here ajk, these are the components of the mixed tensor of second rank in unprimed coordinate system. So first of all, this ajk has been differentiated with respect to xl, which are the variables of the unprimed coordinate system. Okay, and then we will differentiate that variable with respect to a variable in the prime coordinate system, that is x prime sigma. And now we will keep the first factor, that is ajk, at each, and we will operate the operator del x prime nu on the second factor, and the second factor is del xk by del x prime nu. Okay. So this will be del 2xk by del x prime nu times del x prime sigma. Okay. But as you have learnt in my previous lecture, that this second order derivative, that is del 2xj by del x prime mu times del x prime nu, this is defined like this. In terms of the Christoffel symbols, we define this second order partial derivative by this expression you have seen earlier. And in the similar manner, in RHS, this second order derivative will be also defined in the similar manner. I have not written it. We will write the expression for this in our calculation later on. So now let us see. When you will substitute the values for the second order partial derivative, one in LHS here and the another in RHS, then what will be this result? You can easily see. So this first term in LHS is at is, okay, and at the place of del square xj by del x prime mu times del x prime mu, you may write this much, okay, as I have told you, and a dashed mu nu is at is. Now see the terms in RHS. The first term in RHS has been written here identically in the similar manner. Only this del ajk by del xl has been written at the last. Okay, and again, instead of this second order partial derivative, that is del square xk by del x prime nu times del x prime sigma, now you can write this expression, okay, in terms of the Christoffel symbols of the second kind, okay, and this ajk is at each, okay. Now in this equation we will use equation number 2, and we will also make a appropriate change of the dummy indices, okay. So when you will use this equation 2, see here, and change the dummy indices, then this result may be written like this. You can see here actually this see here, yes, this del x j by del x prime lambda and del x prime mu is here. So instead of lambda, now you may write mu, okay. It means lambda is replaced by mu. So in this condition, in LHS, in both terms, this del x prime del xj by del x prime mu, this will be actually written now del xj by del x prime, sorry, del xj by del x prime lambda. Now this will be written as del x prime mu, okay. So you can see then the remaining, this will be just a common factor, and the remaining terms will be like this, okay. And similarly in RHS, you can see when you will take this first term, this will be del xk by del x prime mu times del xl by del x prime sigma, and this del ajk by del xl, okay, this is present here. This factor has been taken as a common factor, okay, because when you will make the proper change of dummy indices and utilize the property of the these symbols, then you can write like this, okay. Now after getting this result, let us take the inner multiplication of this result with del x prime mu by del xj, okay. See here, when you will multiply this partial derivative del xj by del x prime mu by this del x prime mu by del xj, actually that product will be 1. So in LHS your term, the expression is like this, because when you will take the inner multiplication of this term by this del x prime mu by del xj, then the product of del xj by del x prime mu and del x prime by mu by del xj, that will be equal to 1, okay. And in RHS, now you have to take multiplication by this del x prime mu by del xj, and the remaining terms are at each, you can see. Okay. Now we will introduce a comma notation. Okay. And how this comma notation is defined, you can see here. We write a contravariant index A, covariant index J, semicolon L. In fact, it means this is actually the covariant derivative of the tensor AJK with respect to XL. Mark it. The covariant derivative of tensor, mixed tensor AJK with respect to XL. Actually, that is written by this comma symbol. Okay. And we define this expression inside the bracket in RHS of equation 3 by this. Okay. So this del AJK by del XL plus gamma JML AMK minus gamma MKL times AJM. This is written as AJK semicolon L. Okay. So when you will use this equation 4 or this definition in this equation 3, then you can see what you may write instead of this LHS. Actually, this LHS will also then represent a tensor of actually third rank, you will see, and that will be A dashed mu nu with respect to sigma. So see here, A dashed mu nu semicolon sigma. Okay. On the basis of this equation 4, I have written for this for LHS. And in RHS, you can see this factor is actually the common factor here. And instead of the expression inside the bracket on the basis of equation 4, now you will write this much. Okay. So A dashed contravariant index mu, covariant index nu, semicolon sigma, that is equal to this much. Now see this result seriously. Can you say that this equation represents the transformation law for a tensor of what rank? Definitely there are 3 partial derivatives, so this will definitely represent the transformation law of a tensor of rank 3. Okay. And actually this AJK semicolon L, this is called the covariant derivative of the mixed tensor AJK with respect to XL. Okay. So you can see we have defined here the covariant derivative of a second ranked mixed tensor. But the covariant derivative of the second ranked tensor AJK is a tensor of rank 3. So in the beginning of my lecture today, I have told you that whenever you will find the covariant derivative of a tensor, the resulting tensor has a rank just greater the rank of the original tensor by 1. Okay. So I have written here, you can see that this AJKL is a mixed tensor of rank 3, and this is actually called the covariant derivative of AJK with respect to L. Okay. So now you can see this equation A is our final result for the covariant differentiation of a general tensor AJK. Okay. And you can see some important facts which we will observe from this equation, that the covariant derivative of Ajk actually contains three terms. The first is the partial derivative. These are del x prime mu by del xj, del xk by del x prime mu, del xl by del x prime sigma. Okay. Now the term with positive sign similar to that contained in the covariant derivative of a contravariant vector, and the term with negative sign similar to that contained in the covariant derivative of a covariant tensor. In fact, this from this equation 4 we can obtain this. You can see that when we define the covariant derivative of a tensor Ajk with respect to XL, in RHS there are three quantities. First one is the partial derivative of the given tensor with respect to XL. The second term is positive, and this positive sign is just similar to that contained in the covariant derivative of a contravariant vector, which we have learnt in my previous video. And the third term is negative, you can see here. Actually, this negative term is just similar to that contained in the covariant derivative of a covariant vector. Okay, so these terms may be positive or negative in accordance with the indices. Okay. Now, after getting the idea of the covariant derivative of a mixed tensor, now we are going to see how we can find the covariant derivative of fundamental tensors. Actually, the covariant derivative of all the fundamental tensors are 0. So you must remember that whenever you will find the covariant derivative of fundamental tensors, either the covariant fundamental tensor or the contravariant fundamental tensor or the mixed fundamental tensor, you will see that the covariant derivative of all fundamental tensors will be equal to 0. So this is a very remarkable fact. You must remember it. But here I have actually proved all those results. But for your objective type question, you must remember this fact. And this fact will be vividly used when we will study the Einstein's general theory of relativity. Okay? But I have actually explained all these facts. So first of all, we are going to see to show that the covariant derivative of a covariant fundamental tensor, which is denoted by the symbol GJK, will be equal to 0. Okay, this will be 0. But how you can say that the covariant derivative of the covariant fundamental tensor GJK is 0? Let us now see. Okay. In fact, on the basis of this equation 4, in fact, when this equation 4 is generalized, in that condition, on the basis of that very equation, you can write that GJK comma semicolon L. What does it mean? It means this is the covariant derivative of GJK with respect to XL. And how it will be defined on that basis? That this is defined as del GJK by del XL minus gamma superscript MJL. You know this is actually the Christoffel symbol of second kind times GMK. This is the covariant fundamental tensor, and minus gamma MKL times GJM. Okay. This is this equation has been written on the result which we have obtained just now. Okay. Now you can see we will apply actually the definition of the second order Christoffel symbol and the first order Christoffel symbol. And when I have discussed the Christoffel symbol, 3-index Christoffel symbol, then you have seen how these two kinds of Christoffel symbols are related to one another. Okay, and you have seen in that lecture that this product, this Christoffel symbol of second kind times this fundamental tensor GMK, this product is equal to the Christoffel symbol of first kind denoted by the symbol gamma JL comma K. And similarly, this product of the second Christoffel symbol of second kind gamma MKL times fundamental tensor GJM, that is equal to gamma KL comma J. We have seen earlier in our lecture. Now, what is the definition of this first kind of Christoffel symbol? You have learned earlier. So instead of this gamma JL comma K, now you can write this much. You know, this is just the definition of Christoffel symbol of first kind. And again, in the similar manner, for this Christoffel symbol of first kind, you may not write this. Okay, but you know that the covariant fundamental tensor GJK is actually a symmetric tensor. And if it is a symmetric tensor, you can easily say that GJK will be equal to GKJ, GJL will be equal to GLJ, and GLK is equal to GKL. So when you will use this symmetry property in this result, what you will get? You can see here in first term there is GJK by del XL, and here there is G del GKJ by del XL. But as you know that GJK is equal to GKJ, so this first term and this first term will be added, not cancel out, but will be added because both are minus. So this will become del GJK over del XL, 2 times of this much into 1 by 2. So 2 and 2 will cancel out. So the sum of the first two terms will be in fact minus del GJK by del XL. But here you can see this term is also del GJK by del XL, but this is positive. So this term and the sum of these two terms will cancel out. Now let us see GLK and GKL. GLK and GKL. Both are equal, but sign will be opposite. Here GLK by del XJ, this will be actually negative. But here this minus minus will plus, will become plus. So this and this will cancel out. Okay. Again you can see this GJL is equal to GLJ. So this term and this term will also cancel out. So what you are getting? In fact, the all terms in RHS will be cancelled to one another, and finally you can say that this GJK semicolon L, it means the covariant derivative of the fundamental tensor GJK with respect to XL is equal to 0. This fact I have stated earlier, that the covariant derivative of a fundamental covariant tensor is equal to 0. So this fact has been proved, and I think you have clearly understand the calculation. But as I have told you, you must remember this fact for your objective type problems. Okay. Now, in the similar manner, we are going to see to prove that the covariant derivative of a contravariant fundamental tensor, which will be denoted by the symbol G superscript jk, that will be also equal to 0. Covariant derivative of a contravariant fundamental tensor G jk is also equal to 0. But how we can prove it? For this, we will find the partial derivative of the fundamental tensor G jk with respect to x to the power L. Okay? And on the basis of the result obtained earlier, you can say that this will be G jk semicolon L. This is actually the covariant derivative of G jk with respect to L. And on the basis of our previous result, this can be written as del G jk by del xl plus gamma jml times gmk plus gamma kml glm. Okay. Again, we will apply the idea of the Christoffel symbol here. But before that, the product of the covariant fundamental tensor G jk and the contravariant fundamental tensor GKL, this is equal to the Kronecker delta Lj. What is this delta Lj? This is called Kronecker delta. And you also know that this Kronecker delta has two unique values. This Kronecker delta is equal to 1. When it will be 1? Actually, when both of these indices, that is L is equal to J, then Kronecker delta is 1. But if L is not equal to J, then Kronecker delta is simply 0. So Kronecker delta is fixed. Okay, it is either 1 or it is 0. Okay. So now let us differentiate this equation 6, where we have defined the product of the two fundamental tensors, that is the covariant fundamental tensor and the contravariant fundamental tensor, with respect to the variable xp. Again, you can see in LHS there is a product of two functions. So when you will take G jk at each, you must have to differentiate this G superscript kl with respect to xp. So the first term is G jk times del G kl by del xp, and plus, now we will keep the second factor at each, which has been written here, and we will differentiate this G jk with respect to xp. But as this Kronecker delta Lj, this has actually a specific value either 1 or 0, so it is simply constant. And the derivative of a constant will be 0, so in RHS you will have to take 0. Okay. Now for getting the proper result, let us multiply this equation by a contravariant fundamental tensor GJM, and after taking this multiplication, your result will be GJM times GJK times del GKL by del XP, and plus GJM times GKL times del GJK by del XP, and that is equal to 0. Okay. But the product of these two fundamental tensors is simply equal to the Kronecker delta Mk. Okay. Kronecker delta Mk. And this partial derivative is at each. Since here both of the fundamental tensors are contravariant, so you can't write this product equal to Kronecker delta. This is at each. Okay. And del GJK by del XP. Okay. Del GJK by del XP. for this del g jk by del xp, you may write this much. How you can write it? You can see this result. When actually we have defined here this relation. Yes. Actually, this is the property of the fundamental tensor. You can see. So instead of this, you may write like this. Now let us see the product of this GKL and this gamma JPK in accordance with the relation between the Christoffel symbol. This product GKL times gamma JPK, that will be equal to gamma LJP, which is actually the Christoffel symbol of second kind. Okay, and GJM is attached. Now again, the product of GJM and gamma KPJ, that will be equal to gamma MKP. Okay, and here GKL is attached. Okay. Now you know that dummy indices may be freely changed. So in this expression, now let us change the dummy index j to k. It means you must write now k instead of j. So let us see, where there will be j, we will write k. So here there is g superscript jm. So instead of this j, I have written this k. Okay, and instead of l, we will write m. So instead of m, there is l. Okay, and here there will be, sorry, first of all I have written this has been written. Okay, and in this we will make this change of dummy indices. Instead of j, now we will write k. Okay, so this is gmk and gamma ljp, but instead of j we will write k. So this is lkp. Okay, but according to the definition of the covariant derivative of a mixed tensor, we have seen that this expression is as defined in equation 5. This, on the basis of that equation 5, you may write this. This is the covariant derivative of the fundamental tensor GML with respect to XP. Okay, and this will be equal to 0. So you can now, in general, you can say that the covariant derivative of a fundamental tensor GJK with respect to XL is equal to 0. So this was the result which we will have to prove. Now finally, we are going to see that the covariant derivative of a mixed tensor like GJK or delta JK with respect to XL is also 0. Okay, just you have seen that the covariant derivative of this delta JK with respect to XL, that is equal to del delta JK by del XL plus gamma JML delta MK minus gamma MKL delta JM. This has been written on the basis of the previous result. But as you know, the Kronecker delta, this delta JK is a constant, and therefore its derivative will be 0. Okay, and again, when you take m equal to k, then this Kronecker delta will be 1. So therefore, instead of m in this second type of Christoffel symbol, we will have to write here k. So this is gamma j kl. And again here, This Kronecker delta Jm will be also 1 when J and M will be equal. So instead of now this M, we will write J. So this is gamma J KL. Now you can see these two will cancel out and finally our result is 0. So you can see that the covariant derivative of the fundamental tensor delta Jk with respect to L, which is denoted by this symbol delta Jk semicolon L, that is equal to 0. So this is a very remarkable fact, and so finally you can say that the covariant derivative of the fundamental tensor like Gjk or G superscript Jk, it means this Gjk is what? This is the covariant fundamental tensor, and the contravariant fundamental tensor Gjk and the mixed fundamental tensor delta Jk all are the covariant derivative of all these fundamental tensors are 0. Okay. So if their covariant derivatives are 0, you can easily say that the covariant differentiation of all three fundamental tensors can be treated as constants. Okay, and that's why the fundamental tensors, that is Gjk or this are defined as the covariant constants. Okay. Okay, you have now a concrete idea how to find the, in general, the covariant derivative of any tensor of any rank. And in the last of the lecture, we have discussed actually the covariant derivative of fundamental tensors, and you have seen that the covariant derivative of all the fundamental tensors are 0. This is a very remarkable fact. Actually, all these facts will be used in our forthcoming lectures when we will discuss the Einstein's theory of gravitation, that is the Einstein's field equation. Okay, thank you very much.